So we did something called linear regression, and then we did something called gradient boosting, and then we did something called random forest regressor. So every machine learning algorithm comes with different types of tuning knobs. And you know what are the tuning knobs? The tuning knobs are basically certain parameters that you can control in the models. So as you're using these algorithms, these are different parameters you can control. So even this has to be tuned. If I use a different value for these parameters, we will not get very good results. So even this kind of thing we will have to basically control. Okay, and these are the tuning knobs that we are kind of talking about here. So when we come to gradient boosting, you can see right now what I've done. I can use different types of values of estimators. This is the same data set, X train, Y train, X test, Y test. I can start with estimators equal to 1. And very interesting, for the same gradient boosting algorithm for which we got such a good result, the moment I take the value equal to 1, now what is n estimators is something I'm not getting into right now because that's a mathematical thing. We need to study decision trees for that. We'll come to that later. But for now, just remember different algorithms will come with different hyperparameters. They are nothing but tuning knobs. And even that you are trying to control. This is not manually done. There are different tools that you will use for it. So as a developer, when you're trying to build applications, you will have to figure out the right kind of data. You will have to figure out the right kind of algorithm, try out different algorithms and choose from a list. And you will also have to try from the different hyperparameter values. So in this case, you are choosing n estimators, and you will take different values of n estimators and trying to decide which is the best one. So maybe in this case, you take n estimators equal to 1, you get a very poor result. And now you take 2, and you see that as you increase the value, it's like a knob that you tune, right? You can see as you increase it, for the same algorithm, as you take a higher and higher value of n estimators, you see you're getting towards a more and more good fit model. Can you see the training and testing scores are slightly going up? When I take n estimators equal to 3, the scores will slightly go up. When I take n estimators 4, the scores will slightly go up. So as we take different values of n estimators, the scores will increase. Okay, so you can see that when I take an estimators 3, it is 43 and 38. When I take 4, it is 53 and 49. When I take 5, it is 60 and 57. So as we increase the n estimators, the values are actually, the scores are actually improving. The model is becoming better. It's not guaranteed to happen. We have to tune the hyperparameters, and this is how we can uh, choose the ideal value of the hyperparameter. But remember, if you take a very high value of n estimators, this might actually lead to overfitting. What is overfitting? Overfitting is a situation where the training score is very high, but the testing score is very low. So just be cognizant, just be aware of it. Do not take a very high value because if you take a very high value of n estimators, your training accuracy might touch close to 100%. It's also a little slower to run now. Your training accuracy will touch 100%, but your testing score will keep reducing. So this is another thing to keep in mind, that it's a knob that you have to tune. If you make it very less, it will underfit. If you make it very high, it will overfit. You have to choose something in between. And this is a very important thing that everybody should keep in mind as we do a lot of machine learning going forward. Even in deep learning, the same idea will get used a lot. So you will try out, you will experiment with different types of models, take different forms of data, try different algorithms, try different hyperparameters, build different models, and then evaluate on the basis of this thing. Okay, so right now I'll just set it to maybe something like 100, or we can leave it as a default. So this is something that we need to tune. Okay, just keep this at the back of your mind, everybody. One more very important thing I would like to clarify at this point in time is, all this while we were using, and these are all core concepts. Okay, so as we see the demos going forward, the same core concepts will get repeated. Another very important concept I would like to cover is the concept of train and test accuracy, or train and test R squared. Now, we have already discussed it. I know we have already covered what is train R squared, what is test R squared. We know that. We know what is training and testing accuracy. But please understand that whatever we have done now, we have, before we even define the model and everything, we created something called a train test split, right? This is the general workflow that we followed, right? Which we took the whole data, we split the data into training and testing. Pretty much the same work that we covered here, right? If you remember, we take the data, we split our data into training and testing. The problem is there could be bias, there could be some inherent bias in your training data, and there could be some inherent bias in your testing data, right? So what I mean to say is it could be possible, it could be possible that by chance your training data is too easy and your testing data is too difficult. It could happen. I'm not saying that it will happen, but I'm saying it could happen. Because you're doing a random split, right? You are doing a completely random train test split. And because you're doing a completely random train test split, it can absolutely happen that your training data is very easy. So it is very easy to study the topics. But the moment I give you are solving a mock question paper, the question paper is very difficult. So when that kind of thing happens, the testing accuracy and the training accuracies will not give you robust answers. Imagine a real preparation process. Let's say you studied something and you want to evaluate yourself a week before the exams. You want to do some mock sample exercises. You want to do some sample exercises. And when you are attempting the exercises, look at it this way. If your question paper is very difficult, then it won't be the right evaluation. Moreover, it is also important to do multiple evaluations, right? If you are only evaluating based on one mock paper, that is not the right kind of evaluation. So all this while, what I did was I calculated a single training and a single test accuracy, right? So we solved one mock question paper and we saw, okay, I'm getting this kind of a score. I'm getting this kind of an accuracy. But that is not the best indication of the model, right? Best indication of the performance of the model, because what you need to do is you need to evaluate this model on a bigger data set, on a much bigger sample set of mock papers. It is almost like how we conduct an interview in a company. So when you want to interview a person, do you only conduct a single round of interview? Not really, because a single round of interview has higher potential of bias. If you only take a person and ask that person one question, if the person answers the question hired else fired, no, that's not ideal. But you want to, because your test data, it could be biased. So whatever questions you are asking to that person, maybe by chance that person knows all the topics. It could be a fluke hire, right? It could be a wrong hire. So that is the same concept why we do multiple rounds of interview. We take multiple question papers and we solve multiple rounds and we evaluate, take the average. The same applies for machine learning also. So instead of evaluating the model on a single test set and calculating a single accuracy or a single R square in this case, we try to evaluate the performance of the model across multiple train test splits. We try to split the data in different ways. And I'm trying to explain this in a very analogous manner. So imagine we are creating 10 different question papers, and I will ask you whatever model we have got, I will ask that model, and I will try to find the performance of that model across 10 different question papers. How is it performing in the 10 different mock papers? Find out the accuracies, take the average. And that is kind of something I have simulated here. It's not absolutely perfect, but it is kind of something I simulated here. You can see. Okay, so this is exactly what we can do using something called cross validation. Okay, so this is exactly something that we can simulate using something called cross validation. So this is the problem. How do we solve that problem using something called cross validation? So this is the same linear regression algorithm that I can use here right now. So you can just maybe copy the code and paste it here, because this is where we have done the stuff. So let me show you in the same demo. So this is the linear regression part, if you remember. Let me run this code once again so that we are clear. And I will just use that cross validation code. So until here, we are getting a single training and single testing score, which is not ideal. I want to do multiple rounds of interview. So what I can do is I can take the same model, which is model 2. I will use something called cross val score. And if I say CV equal to 10, you will actually get 10 different scores. And now what I can do, I can actually take the average score. Okay, so we can say print the mean score, the average score. Okay, so it is actually giving me everything. Can you see how cool is this? Look at this. This is power of Gemini. So Gemini understands what I want to do. So we have done 10 rounds of interview and we have got 10 different scores for the same linear regression model. we've got 10 different testing scores. And now I want to find out the average testing score and the standard deviation of testing scores. Right, you can ignore standard deviation. That's a little technical, but you can look at average score, and the average is 88.759579%. So next time anybody asks you that, hey, what is the performance of my linear regression model? So you will no longer say that, hey, it is 89.47%, but you would rather say that, okay, the cross validation accuracy or the cross validation R squared of my linear regression model is 88.579%, because this is a more robust number. Because see, sometimes the accuracies can be very high. Fluke chance, right? I told you, because if the question paper is easy, in some splits it is getting 96%, in some splits it is giving 81%. So there is huge variation, but we're taking at the average. Okay, so this is the idea behind what we refer to as cross validation. So these are all different concepts that we are discussing, which will be very similar to every single aspect of the course that we are talking about. So a lot of core ideas we have covered. We talked about machine learning life cycle. We talked about train test split. We talked about overfitting, underfitting. We talked about the idea of building models. What is fit? What is predict? And now we are talking about cross validation. These are all core ideas. So next time, even when we apply a different algorithm, even when we go to deep learning, even when we do classification, because for classification we have different algorithms that we will use, these core ideas will remain very, very similar. Okay, so just keep this at the back of your mind. This is a model evaluation technique. Okay, this is not an algorithm, but what is this? This is actually a model evaluation technique. It gives me a more robust way to evaluate the performance of a model. Okay, it's not evaluating based on a single number, but I'm evaluating based on 10 different numbers and taking the average. Okay, so that's the idea. Rest, I think there are some other samples that I have done. You can go over the other parts of the code. It's a lot of things I've done in this notebook. Not all of it is important or relevant right now. Okay, but some of the other things that I've demonstrated here are pre-processing tasks. For example, you can see this one. So this is a very interesting piece of code that I've shared, which we will use later. So here I have used something called a pipeline, right? So what is a pipeline? A pipeline is basically a, a series of different steps that we are applying. So for example, we have a sales prediction problem. It's a regression problem, right? So the sales prediction problem is ultimately a regression problem. Now, what we want to do here is we want to effectively apply a pipeline. So first, we want to do standard scalar. We want to scale the data, and then we want to do linear regression. So we are effectively framing the problem in two steps. Okay, so can you see what we are doing? We are basically framing the problem in two steps right now. So first, we are applying a linear standard scalar. Standard scalar is like a scaling technique. Okay, so some of you who have you can think of standard scalar as like a scaling technique. So first we are applying standard scalar. We are scaling the data. So we are converting all the data to the same scales. And what is it? See, because different values can be in different scales, right? So some values can be, imagine if you look at experience and salary. Think of that use case. Think of experience and salary as the two use cases. So some values can be very high and some values can be very small, right? So if you think of the same, experience and salary kind of use case, so we can have a scenario where the experience of a person usually will be the experience of a person usually will be very small, right? It will be either from 1 year to 50 years like that. Experience will range from something like 1 to 50, right? Not more than that. But the salary of a person will typically range from salary of a person might typically range all the way from 1 to 100,000, 100 million, $10 million, whatever. So the salary will be ranging over a larger range. So what you want to do, what we really want to achieve here is we want to go and convert our data into the same scales. And sometimes we have seen it is better on the algorithms, it's better on the models. The models tend to be better, they tend to be more robust, they perform well when we scale the data. So just remember, as a standard practice, whenever we apply any of the models in our case studies going forward, we will always try to make it a point to scale the data. It's a good practice. And then we will apply the algorithm. That is what the pipeline will do. So this is what we call a pre-processing stage. Okay, so when we say data pre-processing means that before you apply the models, before you apply the different models, you will first pre-process the data, right? So first you will pre-process the data, and then you will apply the different models. So these are the two phases that we are talking about. So first step we will go and pre-process the data, and then we are applying the different models here. So that's the way. Okay. This is what we did in the pipeline. So there are two, these are called steps in a pipeline. This is step one. You can see this is the pipeline, and the pipeline basically has two steps, right? So again, you have the pipeline, and this particular pipeline, there are two steps in the pipeline, and you can clearly see the first step is standard scalar. This is a step name. You can give any variable name. This is a step name, and this is what the step is supposed to do, the step class. And this is the second variable name, LR. You can give any variable name, and this is a step class, which is linear regression. So pipeline can consist of multiple steps. And if you want to see a sample pipeline, you can actually see build a. I mean, I can run the code. I mean, we already seen these things, right? So pretty simple. And now you can use Gemini because we have this in the context. We can say build a complex pipeline consisting of multiple pre-processing. Just to show you an example of how a pipeline looks like, multiple pre-processing steps and ending with a linear regression model. You'll see that when the pipeline gets built, initially you will have multiple pre-processing steps. It will do everything for me. And here we did multiple things, like we have standard scalar, we did something called power transformer. And power transformer is basically used to normalize the data. It's another kind of transformation, and then linear regression. So see, this is how the pipeline looks like. So define the pipeline with multiple pre-processing steps. So we're first taking the data, we're first scaling it, we're transforming it. This is like a normalization technique, and then we are applying the algorithm. Rest of the part is exactly the same: train, test, split, dot fit, and then dot score. Okay, so this is the simple way. I think there's a lot of commenting that is done, but I don't think there's anything complex about this pipeline. Very simple, but you can go and add some more detail consisting of multiple pre-processing steps, feature selection steps. If you want to really see a complex pipeline and ending with linear regression model, build a complex. No, so the more details that you make it, the better your thing will be. And maybe if I do it this way, I'll get a more detailed pipeline. This is a very, very complex one. So here, what we have done is we have actually got two pipelines. So can you see? So this is a pre-processor pipeline, and this pipeline is used in this pipeline. So this is again, it's one of the magics of Python, where we can kind of it's like divide and conquer. So you create one pipeline that will only do the pre-processing, and then you will use the pre-processor pipeline inside another major pipeline. So first you are pre-processing, then you are doing feature selection, then you are doing linear regression. So this is how you will build your workflows going forward, right? But I hope you get the ideas. What we are trying to do in these trainings is we are trying to get the idea. What is it? What are the core concepts? So next time you see a code like this, you know what is it? You know the relationship. Okay, so we are just trying to build these spatial relationships in the human brain so that we understand this is this, this is this, this is this. So once you know that, you can build literally everything. Okay. So now moving on, I think these are some demos on pipelines that we have done. You can go over it. And the last part that I wanted to talk about towards the end is this thing. Okay, I was explaining about estimators, and remember, this n estimators is typically called the hyperparameter. Okay, so I've already covered this up, but just to briefly recap this idea, this is called a hyperparameter. What is it called? It's called a hyperparameter. So this is called a hyperparameter. That's what you're able to see on the screen right now. Okay. So we try different values of estimators. So along the x-axis, you have something called estimators. Along the y-axis, you have something called score. Okay, so x-axis, you have something called estimators. Y-axis, you have something called score. So We try different values of estimators and we build different models, and we see which model is giving us the best accuracy. So we can clearly see that as the estimator's value is less, and I think I already demoed that some time back, you see that when the estimator's value is equal to 1, the model is significantly underfitting. You see the training and testing scores are both very low. In fact, we call it the cross-validation score. We discussed about that. What is the cross-validation score? So we can see the training and cross-validation scores are very low when the estimators is equal to 1. And as the estimators increases, the training and cross-validation scores are both going up. So as the estimators increases, as we have more and more estimators, as the as we increase the value of the tuning knob, you can see that the training and the validation scores both tend to increase. So the training and testing scores both tend to increase as the estimators are going up. And this is the graph that we discussed, underfitting here, overfitting here. And we are trying to find out the good fit zone somewhere here. Okay, usually the graph, if you go further enough, you will see something like this. So if I use a different color, the blue is the validation score, the testing score. The testing score will usually tend to drop. The testing score will usually tend to drop. And after a while, the training score will continue increasing. This is the orange. The training score will keep going like this. This is the pattern we'll generally see. Right. So as you increase the estimators beyond the point, the training will touch 100% and it will remain there, but the testing will tend to drop. And you're typically trying to find the sweet spot, which is somewhere here. This is the good fit that you're trying to find. But remember, overfitting, underfitting, and good fit are very relative concepts. So we will never say that we have a perfectly overfit model, a perfectly underfit model, a perfectly good fit model, but we will always make relative comparisons. We'll always say that, hey, this model is more overfit, this model is more underfit, and this model is more good fit.